So, with environment protection and sustainability production concept, renewable energy generation and its integration is going to play an important role. So, our next speaker, Professor J.B Ekanayake, is the Chair Professor, Electrical and Electronic Engineering of University of Peradeniya. He obtained his PhD from the University of Manchester Institute of Science and Technology, United Kingdom. He is a renowned academic with multiple publications about renewable energy. In addition, Professor J.B is also the Vice Chairman of the Public Utilities Commission of Sri Lanka, and he has a high level of expertise in renewable energy generation and its integration. So, I warmly invite Professor J.B Ekanayake to the digital podium to enlighten our audience regarding the renewable energy. Sir, the podium is up to you.
Thank you very much, Vidura. And thank you, everybody, for inviting me, especially the organizing committee of the Techno Meetup. Let me first share my screen. Can you see my screen properly?
Yes, sir, we can see.
Oh, thank you. Right. Let me... Okay. Now, those who has been listening to the last two speakers, Michelle and Gamini, must have seen that we are talking about a very broad topic. The topic that I'm going to talk about is, a completely different aspect, but Gamini in two places link that into the sustainable production, and also you saw that how the renewables, so the low carbon emitting technologies can protect the environment. So here I will be talking about the renewable energy generation, and more importantly, its integration, because the generation part is easy. The difficult part is the integration part. So the content of my presentation is sustainable energy future. I will particularly talk about how the renewables can support, then wind energy, solar energy. These two energy sources I picked because they are the fast growing energy sources, and to give an insight for particularly for the students who are joining us today, how they work. Then barriers for achieving a sustainable electrical energy future, and how we can support a high penetration of renewable, thus sustainable electrical energy future. So let's talk about the sustainable energy future. Now what you are seeing here is the economic growth and the energy growth starting from 1850 to 2016. You can see that at the very beginning, when the industrialization started, everything was more or less renewables. We had energy, largely biomass, and some places use the water wheels and so on. But the global and local transport networks, mainly fueled by coal and oil, took up the share of non-renewables, mainly fossil fuel, and by 1950 you can see that the portion of renewables has gone down. Then came the unprecedented rise in Western living standard and the rapid industrialization of China. And you can see that those two economic growth periods were followed by heavy use of fossil fuels such as oil, gas, and coal. And the renewable became a smaller portion in the world. But that's not what we want. What we want is a growth in economy while keeping the while having more renewable use and minimizing the energy use. So the rapid increase of energy should be somehow flattened. So we need to, in order to achieve this, we need marked increase in energy efficiency. We need rise of electrification, more efficient ways to meet energy needs in many applications such as combined heat and power, then electric vehicles, then heat pumps and so on. Then the growing use of renewables. And I'm talking about this third aspect, which is the growing use of renewables, how you can achieve that and how you can integrate more renewable into our power system. So let's move on to the most prominent renewable energy sources available in front of us. The wind energy. The wind energy is one of the highest growing energy sources. And in order to explain you how a wind turbine works, let me take you to a simple aircraft. Now, when the aircraft moves in this direction very fast on a runaway, the air goes in the reverse direction, and the blades are formed such that the bottom side of the blade is having a shorter distance to travel, whereas the top side has a longer distance. So the air in the bottom side travels less distance, whereas the air in the top has to travel longer. So you can see that there is a pressure drop developed on the upper side, which will basically lift your aircraft. And that is how the aircraft works. So this exactly the same scenario is used for wind turbines, but in this case, we use the lift force, but not to lift the wind turbine, but to make it rotate. So you can see that the lift force acting on the rotor blades rotate the rotor. So basically, most of the wind turbines out there are because of the lift in forces. The drag is basically bend the blade towards the tower. And with bit of physics, you can prove that the power generated by a wind turbine is given by this equation, where the P depends on the wind speed, which is the most dominant factor here, the wind speed into cube, which is the most dominant factor. Then rotor diameter, the area swept by the rotor is determined by the rotor diameter. Lambda, which is kind of a parameter, it's based on the rotational speed of the generator and the wind speed. And the beta is the pitch angle, which is actually how the blade pitches. So, so you can see that in order to extract more power over the time, we initially had the fixed speed machines, but in fixed speed machines, the lambda cannot be operated at its optimum. The reason is with the wind speed, you need to change the omega to get an optimum lambda value. So we started move on to the variable speed, and also you can see the area has increased, the swept area has increased by making the rotor diameter higher and higher. Today, you can get a large wind turbines. The offshore wind turbines are as big as 50 megawatt and using very different technologies to what we had. And you can also compare the size of the wind turbine with the largest aircraft available, which is the Airbus A380. So you can just imagine a size of today's wind turbine, each generating 15 megawatt. Now, one thing about wind turbine is they do not operate when the wind speed is below a certain speed. We call it the cut-in wind speed. They are basically stopped because no point of generating. The whatever you generate will be lost inside the turbine as losses. Then as the wind speed increases, the power increases as per the equation that I showed you in a cubic function of the wind speed. But when it reaches the rated power of the turbine, you use various techniques to get rid of the power available in the wind and trying to make the power output constant. At around 25 meters per second, where the wind turbine cannot tolerate any more wind gust, the wind turbine is the turbine blades are braked and the turbine is stopped. So this is the typical. So if you have seen a wind turbine which is not rotating, don't think that there's no wind. It is because the wind is less than 3.5 or greater than 25 meters per second. Moving on to the next promising energy option, which is the solar energy. There are many options available to us. There are wafer-based technologies and thin film technology. The wafer-based technologies are the crystalline silicon, gallium arsenide, and something is coming up. You can regain control at any time by, I don't know what it is. I'm going to decline it. So anybody from the, it says Tyrone Davis. Do anybody knows him? He's asking remote control of my screen. Anybody who is in our audience? Anyway, it's keep on coming. That's my issue. Let me see whether it stopped now. So the third wafer-based technology is the multi-junction, which I will show you in a minute. Then there are thin film based. There are commercially available thin film technologies are the amorphous silicon, cadmium telluride, cadmium indium gallium sulfate or something, and the quantum, no, I can't remember what is EZTS. Then there are emerging thin film technologies, which are the perovskite, organic, diselenide, and the quantum dot. Now, these are not yet come to the market. They are there, but not in mass scale used in applications. Now, the multi-junction is one which use prism to break the sunlight into various portion of our wavelength. Usually, the gallium indium phosphate is good for low wavelength. Then the silicon is good for wavelength up to around 1000 nanometers. Beyond that, it is the germanium. So what this multi-junction use, it uses a gallium indium phosphate, gallium arsenide, and germanium cell sandwiched with the prism. So the sunlight with the right wavelength is sent to the different portion of the multi-junction PV cells. By doing that, you can obtain a very good efficiency. If you look at the NERL, they keep on updating this picture. The multi-junction has now reached a laboratory cell efficiencies of around 48%. Our silicon, which is the most commonly used technology in the world, is having the efficiency of half of that. And you can see that this new guy, the perovskite. Now, for silicon to reach that 20 odd percentage. It took so many decades, but perovskite has started, or they found that material somewhere in 2013 and now reached the efficiencies of silicon. Forgive me if I'm pronouncing the word wrongly. If there's a Russian person, I'm sure he will be laughing at me. And when you look at the cost of PV system, you can see that the cost of the residential and the commercial or the grid connected PV both has come down. For residential, it's now around 2.71 per kilowatt peak, and for utility scale, it is around less than $1. And this figure shows various cost components. Right. I think that this is the most important part I want to discuss. We have a best energy sources surrounding us, the wind, solar. Why aren't we harnessing all of them? If we harness all of them, there won't be coal power. There won't be any other environmentally hazardous gases emitting from the electrical sector. So we will have a sustainable electrical energy future. But there are a lot of barriers to achieve that. Now, what you are seeing here is from from particular area in South Australian network, part of Queensland area. And you can see over the years, this is 2006, this is the demand seen by the national grid. But over the years, the demand seen by the national grid has this duck shape. I don't know whether they also call it duck. The Americans are calling duck curve. And you can see that in 2019, the daytime, which is the time where the solar PV is maximum, the demand of this particular the customers, it's a South Australian power network minimum loads, has gone down from around 953 megawatt to around 62 megawatt. This is because of the high penetration of rooftop solar. Now one can see this as a good thing. But the main problem is the utility, which is maintaining the power during the night, as well as keeping the system stable during the daytime, does not see this demand. This is a latent demand which they don't have any visibility. That is one of the key problems for integrating renewables. And the other issue is this is creating some inflexible power plants to turn off. For example, here you can see 1 week in UK, the coal power generation from Friday 21st April 2017, the first time in the UK history, they have to completely turn off their coal power plants by 24 hours. And even in the other days, you can see that coal power is only operating for a couple of hours. They have to do daily cycling of coal power plant. This is very difficult because there are rise times and the ramp up time and startup times, as also the shutdown times are high. And because of those inflexibilities, operating a power system with these kind of power plants and with renewables which do not have the right visibility is going to be a nightmare for the grid operator. And this is again from Japan. Now, of course, you can see that the thermal generation was very small, but the red line is the load, and the PV generation was very high, but of course they are having pump hydros and some batteries to absorb any excess renewables. So that is, but still, you can see that even with the pump hydros and batteries, they have to curtail nearly 1 gigawatt of renewable energy. Now, that is a must when you go into a high renewable penetration scenario in order to match the demand and supply. In Sri Lanka, also thinking of 70% renewables by 2030. This is the Sri Lankan government aspiration. Whereas the CB and Sustainable Energy Authority is working towards 50% renewables from 2022 onwards, which means in 2022, we will have 1,000 megawatt. This will be looking like this. And this large chunk in the middle is the solar. And we will not have, as in the case of Japan, a large storage to keep this. So what we need is we need to go with what we call the reserve. I'll show it to you in a minute. The main problem what we are facing is we operate, our unit commitment is, I think, weekly ahead, but our economic dispatch is day ahead. That means you plan what power plant to be dispatched, what time of the day for tomorrow by today midnight. Now, if you are going to do that way, then in order to maintain the demand and supply, as I showed you, you will need, I'll go to the next slide and come back to this one. You will need large reserve to be maintained. This reserve is so many megawatt of spinning machines which are not generating any power. And also you can see that there are prediction errors. Even if you can predict the solar PV properly, here you can see that in Japan, they were predicting solar by that much of solar, but solar didn't come that much. There was a deficit of 3 to 5 gigawatt, because of the prediction error. Also, they were predicting the load like that, but load didn't come all the way. It had a surplus. So the dotted line is the predicted load, and the black line is the real load. And you can see that load was also not. And also the solar can do very difficult to balance power fluctuation due to the cloud cover. So because of these reasons, if we are to run a system, we cannot work with the day-ahead economic dispatch. We need to go for short term. Now here you can see that this blue curve and this purple curve is for 4-hour dispatch. And you can very clearly see the 4-hour dispatch is reducing the reserve requirement in most of the time, and it only required for little time. Now I am getting a similar message from a person called Fora. This is the first time I'm experiencing this kind of issue when I'm doing a presentation, and I have to keep on pressing the declining to stop that happening. I don't know whether the organizers can do something.
So can you specify the name of the person?
It says Fora. It looks like, I don't know, not. They are asking the control of my screen. I don't know. Okay. Now, another issue is the local issue, which is basically the increase in the voltage. Now, what you are seeing here is the graph on your left-hand side is the voltage at A phase over the time in one of the German feeders. And on your left-hand side, it says the power flows in that feeder. Early morning, when now it's a Neil Johnson is asking the remote control. I don't know what's, this is the first time somebody is trying to get into my machine while I'm doing this. It's a nuisance, really. Right. Now, in the early morning, you can see the feeder is bringing power from the grid somewhere around 1,500 kilowatt. And as the solar is picking up, somewhere around 10 a.m., the power flows in the feeder becomes 0. And you can see that the voltage is slowly rising. And then the solar, there is more excess solar generation. So the power becomes reverse, and we call it a reverse power flow. And the voltage has gone really up. And when voltage is gone really up, sometimes like in Germany, the limit is 10% and plus 10%, and it has almost reached that level. And also you can see during a cloud cover, the solar output has reduced drastically, which will immediately seen in the voltage. Now, this is again a similar graph, but shown in South Australia. This is 4,000 LV measurement sites in Queensland, and they have 1,115 measurements for for three phases, taken 10-minute average voltage, and you can see that the 99% voltage has gone up in around 204 sites, these sites, where the voltage is greater than the statutory limit. So this is a real problem for renewable integration. So how can we stop this? Now in Australia, they are running a virtual power plant trial. The virtual power plant is, because you cannot have the visibility of a single power plant, you ask many power plants to get together, the houses, and create one single entity. And here in this Salisbury case, they have 100 residential customers on this virtual power plant. This power plant has, this is one of the houses. It has 90 Tesla batteries, each 6.4 kilowatt hour, 10 Samsung batteries, new and existing solar. These are the solar inverters, and local reposite controllers where customer internet aggregated VPP, the virtual power plant. So this is one way. So you will have visibility of these 100 customers collectively, not individually, collectively. That's good enough, because system operator doesn't need to know what's happening individually. And this kind of an VPP will allow you to do the shifting. You can see that during the daytime, the excess energy is stored in the batteries and used in the night by minimizing the power drawn to that VPP from the grid. So that's one solution. Then IEEE 1547, the latest edition, asking reactive power capability of all the inverters. We call it smart inverter. And depending on different category of inverters, which I don't want to go into detail, different reactive power control modes are requested. So what normally you do is your SCADA RTU will receive messages from somewhere asking for reactive power support from the system controller or from the local controller. Then there is a site controller which will dispatch that message to every PV. And the PVs then will provide the reactive power. And also these site controllers can ask for curtailment of the PV. So the reactive power control and curtailment. Remember, this inverter and this inductor can act as a STATCOM, static quark compensator, providing both absorbing and generating reactive power. Now, this is what requested by the IEEE 1547 from a smart inverter. As you can see, when the P is 0, you can use the entire capacity of the inverter for reactive power compensation. However, it doesn't, the IEEE 1547 doesn't ask for that. It asks from 5% of the rated power, you are supposed to give plus or minus 11% of the rated value of reactive power. Then it linearly increases up to 20% of PR. Then you are supposed to give 44% of the capability of your inverter as reactive power. So these are the 4 modes it's defined: the constant power factor mode, voltage reactive power mode, where the reactive power output is used. There's a dead band and 2 droops for controlling. Then the active power reactive power mode and the constant reactive power mode. And you can see some simulations we did in a Malaysian network, which has 120 consumers connected via 11 kV to 433 kV transformer, 1 MVA. This is the load profile is given in blue, and the solar generation within the network is given by this dotted purple area. And you can see that without any voltage control, some of the customers will see the voltage above the statutory limit during the day, midday. Whereas you can use fixed power factor control or the volt power control to bring the voltages below the statutory limit. And you can see from here how each method performs. And in Australia, they also ask for quick frequency power response from these inverters. Now here, somewhere around 1:11 p.m., the frequency suddenly goes above their control frequency limit to 50.86. With that, there was a sudden request to reduce the solar output, and you can see that the green one is for 30 to 100 kilowatt larger sites, where it reduces and then pick it up when the frequency reduces to 50, and the blue one is for less than 30 kilowatts. So you can see that the inverters are supposed to support both voltage and frequency. But of course, the best solution, if you have enough energy storage, you can do wonders. You can see in South Australia, they have this Tesla utility scale energy storage installed, which can do any frequency duties very quickly. And South Australia plans to add more storage. Even the California has mandate to connect storage. And one good thing is the prices of storage also coming down. I'm sure my time is almost finishing. This is a power plant in Japan, Rikasho. Again, I may be pronouncing it not properly. It's a wind turbine plant having 51 megawatt of wind turbines, which has a battery bank of 34 megawatt sodium sulfur battery. And if you have that, you can, now this black line is the dispatch order. The yellow one is the wind farm output. So when the wind farm output is above the dispatch order, you charge the battery and try to keep the total power from that site at the dispatch order. So you can do anything. Your energy storage is pretty fast to achieve good dynamic to achieve this. I'll skip this. Okay, maybe it's last slide. So let me, now in the UK, they also use a technique called conservative voltage reduction. Remember, when you reduce the voltage towards the lower statutory limit, your power output, we remember if it is a resistive load, the power output is V squared over R. So if you reduce the V, the power output also, so power consumed by the resistive loads also reducing. So that used in the UK to reduce or support the frequency events. So these are some of the issues and some of the solutions. Remember, if one need to talk about the issues and solutions, I may need full module to talk about it. In fact, we run similar modules in universities. I do teach at Cardiff University, and we have one module called Renewable Integration, which is a 15-week full module. So it's a huge subject area, which I'm trying to compress within this 30 minutes. I've taken a little more time of yours. Sorry for that. So thank you for listening.
So thank you, Professor. Actually, apologies from our side on behalf of the organization committee. So due to the disturbance from the audience. So thank you for valuable input. So with this consecutive valuable knowledge being shared, I think you all have a great understanding of today's theme and what was happening.